Let me now give you some basic properties of Riemann integrals. I will start with a property that might seem quite silly, but nevertheless it is good to note down, and it is so silly I am going to call it property 0. So, the function f of x equals c, the constant function, is Riemann integrable on every interval a b. And what is its Riemann integral? The integral from a to b of c dx is just b minus a times c. Geometrically, this is just seeing that the area of a rectangle is the base into the height. But you can actually prove this very easily. You take any partition of the interval a b, the upper sum and the lower sum both are going to be b minus a times c. And so, to follow that this function is Riemann integrable with this b minus a times c as its integral. Okay, let us come to something a little less silly now. So, if f and g are both Riemann integrable on the closed interval a b, then so is f plus g. And what is the integral? The integral is integral of a to b of f of x plus g of x dx is equal to integral from a to b f of x dx plus the integral from a to b of g of x dx. I am sure most of you have already been using this property to compute your integrals for a long time now, but we will see shortly how this follows exactly from the definition of the Riemann integral. So, we will give a proof, a mathematical proof. In the same spirit, if f is Riemann integrable on a b, and c is any constant, then the scaled function c times f is also Riemann integrable on a b. And what is its integral? The integral from a to b of c times fx dx is c times integral from a to b fx dx. It is not true that if you take the product of two functions, then the Riemann integral of the product is the product of the Riemann integrals. This is I mean, this is not even true for the derivatives, right. So, there is no reason why you should think that that would be true for integrals. The third property, which is something of a slightly different nature, is about combining intervals. So, suppose we have three numbers now, a less than b less than c, f is Riemann integrable on both the intervals a b and on the interval b c. Then f will be Riemann integrable on the combined interval a c. and what we have is uh, the integral from a to c f of x dx is going to be the sum of the integrals from a to b f of x dx and the integral b to c f of x dx. Again, this property should not surprise you because the integral from a to c f of x dx is the area under the curve, under the graph of f between a and c, but you can break that area up into two smaller areas, the area between a and b and the area between b and c. Let me give you a proof. I already explained to you how to prove the zeroth property, the integral of the constant function. You should try to think about it a bit more and make sure you have understood that. Let us prove the first property, that the sum of Riemann integrable functions is Riemann integrable and the integral is actually the sum of the integrals. So, firstly we need to prove that the sum is Riemann integrable. So, how will I prove that the sum is Riemann integrable? Remember that a function is Riemann integrable if for every real number epsilon greater than 0, you can find a partition P such that UFP minus LFP is less than epsilon. So, you need to find a partition for every P. Now, we know that f and g are Riemann integrable and we need to find show that f plus g is Riemann integrable. So, since we know that f is Riemann integrable, so let us say we are given epsilon greater than 0, since f is Riemann integrable on the closed interval a b, I can find a partition, let us call it Pf of the closed interval a b such that u f p f minus l f p f is less than epsilon by 2. I will make it half of that because finally when I work with f, these will add up. And similarly, there exists partition Pg of AB such that U G Pg minus L G Pg is less than epsilon by 2. Now, I want a partition for f such that u f plus g such that u f plus gp minus l f plus gp is less than epsilon. So, what I will do is I will take a common refinement of the partitions pf and pg. So, what I will do is let p be the partition pf union pg. So, I take all the sub points which subdivide the interval AB in PF, the points which subdivide the interval AB in PG, and I take their union, and that gives me a partition which refines both PF and PG. And what we have is U of F plus G comma P. Well, let us be a little careful here. So, the first step I want to claim is that this is less than or equal to U of Fp plus U of Gp. Okay, why is this the case? Well, it follows from the following very simple fact. So, that if I take supremum of f of x plus g of x, where x is in some set I, this is less than or equal to supremum of f of x where x is in I and plus supremum of g of x where x is in I. Okay, I'll leave the proof of this as a simple exercise in logic to you, and from this it will follow that the upper sum for f plus g is less than or equal to the upper sum for f plus the upper sum for g. And now we have seen what happens to upper sums under refinement of partitions. Well, this is certainly, since this partition P refines Pf, this is going to be less than or equal to U f Pf. And since the partition P refines Pg, this is going to be less than or equal to U of G Pg. So, what we have shown is that U of f plus Gp is less than or equal to U of f Pf plus U of G Pg. Similarly, you can show that L of f plus G P is greater than or equal to L of f Pf plus L of G Pg. And so, you can conclude from these two inequalities that U of f plus G P minus L of f plus G P is less than or equal to U of f Pf minus L of f Pf plus U of G Pg minus L of G Pg. But this U of f Pf minus L of f Pf, well, that is less than epsilon by 2, and U of G Pg minus L of G Pg is also less than epsilon by 2. So, the U of f plus Gp minus L of f plus Gp is less than epsilon. And so, we see that the function f plus g is also Riemann integrable. And so, it follows that f plus g is Riemann integrable on the interval a b. But these inequalities will actually let us completely determine what the integral is as well. You see, when I prove this inequality, U of f plus g comma p is less than or equal to U of f Pf plus U of g comma Pg. This, I did not use any special properties of the partitions Pf or Pg. I did not use the fact that UFPF minus LFPF is less than epsilon by 2 or anything like that. This is true for any partitions Pf and Pg of the closed interval AB, provided I take P to be the union of those partitions, right, the common refinement of those partitions. This inequality will still hold. So, in fact, if you look at the Riemann integral from a to b f of x plus g of x dx, well, that is the infimum over all partitions, let us say q of u of f plus g comma q. Now, certainly this is less than or equal to u of f plus g comma p, the p that I have taken here, which is less than or equal to u of f Pf plus u of g comma Pg. For any partition Pf of any partitions Pf and Pg of the closed interval AB. And so, it follows, since the integral of f is the infimum of the u f Pf and the infimum the integral of g is the infimum of the u g Pg, it follows that integral from a to b f of x plus gx dx is less than or equal to the infimum of these. So, this is integral from a to b f of x dx plus the integral from a to b g of x dx. Using lower sums, you can reverse this inequality using the same reasoning. So, we get the same inequality with the direction reversed, and so it follows that equality holds. Is equal to the integral from a to b f of x dx plus the integral from a to b g of x dx. Why don't you try to prove the other properties of the Riemann integral that I have given from first principles using similar tricks.